Dear students, this is Professor Manoranjan Singha, Department of Mathematics, University of North Bengal, India. Welcome to the third clip. In the second clip, we have seen metric spaces. In case of metric spaces, sequential compactness, countable compactness, unit point compactness are all equivalent. Fine. And today we will extend this lecture, but before going to such extension, let us recall a brief history of metrizable spaces. Topology is a collection whose members are open set, so it is a direct source of open sets. In metric space we can define open sets, so we can construct a collection of open sets. So metric spaces are indirect source of open sets, we can say roughly. Actually, a set where one can talk about open sets is nothing but topological space, and in this sense metric spaces are also topological space. Now, if we are given with a topological space X, this is topological space X, the question is, can it be always possible to find a metric D on X such that the open sets in this metric space are precisely the open sets in this topological space? If it happens, then we say that this topological space is metrizable. Thus, if a topological space is metrizable, then we can say that this topological space is nothing but a metric space Ht for some suitable metric D on X, which induces all the open sets in the topological space X. Fine. For example, R with usual topology. We know the open sets confined within this usual topology on R can be derived from this metric mod of x minus y for all x, y in R. So this R with usual topology is nothing but the metric space R with the standard metric. Okay. Similarly, if we consider Rn with product topology or box topology, same in case of finite product, So if we consider Rn with product topology, then the open sets in this Rn can be generated by this metric dxy root over summation I equal to 1 to n is xi minus yi whole square for all x, x1, x2 dot xn, y, y1, y2 dot yn in Rn. So Rn with product or box topology is also metrizable because open sets in Rn can be obtained via this metric D. In particular, the set of complex numbers, open sets in C. So this is also a topological space. Okay, and the topology on C can be generated by the metric this Z1, Z2, dZ1, Z2 mod of Z1 minus Z2. So it is nothing but this x1 minus y1 whole square plus x2 minus y2 whole square, where Z1 equal to x1 plus I x2 and Z2 equal to y1 plus I y2, within C. Okay, this is a particular form of this, you can see. Not only that, if we consider denumerable product of R with itself, okay, that is countably infinite product of R with itself, and if we consider the product topology on R omega, then it is also metrizable. That is, the open sets in this R omega with product topology can be generated by a metric D, and one of such metric is this dxy is the supremum of this d bar xn yn by n over this. Okay, where this d bar is the standard boundary metric on R, that is d bar xn yn, it is nothing but minimum of 1 comma mod of xn minus yn. Okay, fine. But if we consider R omega, same R omega with box topology, or Rj even with product topology, and the well-known spaces I raised to I we have used in the first or second clip, in the first clip most probably. S omega we have used in the first clip. Okay, R with tau d. Okay, R with co-countable topology or co-finite topology. None of them are metrizable. How? Because we have seen, at least in these spaces, we have seen one more RL not metrizable. Okay, we have seen that in this case, in this spaces, sequential compactness, limit point compactness, countable compactness are not equivalent, so they cannot be metrizable. Okay, because they are not behave like metric spaces. Okay, there is one more tool to check whether a topological space is metrizable or not. You know, we have proved sequence lemma. By using sequence lemma also, we can check that these are not metrizable. Okay, fine. Now the question is, why we will check metrizability of a topological space? What is the necessity? I will conclude this history part, okay, for the time being, by showing that in metrizable space, how a problem can be sorted out easily. Okay, so you know Eurytion's lemma. Eurytion's lemma. Okay, the most important and interesting. Okay, which says that if a topological space X is normal, okay, then for every pair of disjoint closed sets, there exists a continuous map F from X to 0, 1 that maps C to singleton 0 and D to singleton 1. Okay, and while proving this lemma, we have faced uh, many hard situation. No, we have constructed infinitely many sets, okay, satisfying some interesting properties. Then we have taken help of the infimum map. Then we have defined this mapping F. Okay, then we have shown the continuity of F, and it was also a hard job, isn't it? But we'll see that if X is metrizable, then we can construct such a function easily. Okay, that is, if X is metrizable, what does it mean? That is, there exists a metric D on the underlying set X such that the open sets in HD and open sets in X are same. Okay, so the topology here is the collection of open sets in this metric space. Fine. Now since it is T4, so this X is T4, that is X is normal. So X is normal. Fine. Let C and D both are closed and they are disjoint. Okay, they are disjoint. Fine. Now you know the distance function, distance of a point from a particular set A. If A is a subset of X, we can define distance function, distance of a point of any point of capital X from this set A. Okay, this will give you a real number, and it is defined in this way for any point X of A. It is nothing but infimum of, just like this in case of R2. In case of R2, you know, this is a point X and this is A. Okay, take any point A, this, measure all possible distances, and the infimum one is the distance of this point from this set. Same thing, infimum of dxa, where A in capital A. Fine. Okay, this function is continuous. You can check it easily by using the triangle inequality. Okay, fine. You can see the books of Mankers also. Fine. So this function is continuous, and we know this dxa is 0 if and only if X belongs to A bar. Okay, so this function is continuous, and this, by using these two facts, we can define this function easily. How? Just define function f, okay, from X to, it will be 0, 1, because it is defined in this way. Fx is dxc by dxc plus dx d for all x in X. Obviously it will not exceed 1, and all are positive, so this cannot be negative. Okay, now this is the metric space XD or metrizable space X same. Okay, this is C, this is D. If we take any point X from this capital X, then X may be in C, then it will not be in D because they are disjoint. Okay, so if X in C then x not in D, and D means since D is closed, so D equal to D bar. So x not in D bar, and this implies dxd not equal to 0. Okay, because dx is 0 if and only if x in a bar. Since x not in D bar, so dxd cannot be 0. And so dxc plus dxd, this is not equal to 0. Similarly, if x in D but not in C, then dxc will be not equal to 0. Okay, and so this is not equal to 0. And if x neither in C nor in D, both will be positive. So this denominator is actually greater than 0 always. So this function is well defined. Fine. Okay. Now this function is continuous because this function is continuous. So this is a question of two continuous maps. Okay, so f is continuous. Fine. Now obviously f of c, if we take x from C, okay, for all x in C, the fx will be, since x in C, so it is 0, so 0 by this, so 0. Okay, and for all x in D, the fx, x in D means this is 0, but dxc not equal to 0 we have seen, so this will be 1, this will be 1. Okay, so this implies f of c is singleton 0, f of d is singleton 1. So simply we can construct this function if the space is metriable, and this is one of the reason behind searching this kind of spaces. Okay, now let me introduce you to new concepts, okay, that will be used in the sequel, okay, in proving some next theorems. So first let me introduce you Lebesgue number. Lebesgue number, it is number related to open cover of a metric space. So let script C be an open cover of a metric space HD. Fine. So a real number delta greater than 0 such that every subset A of X having diameter of a set means if this is a circle, its diameter is, let's take any 2 points of this circle and measure their distance. Okay, if you take any 2 points and measure their distance, okay, we will get a set of real numbers. Now the supremum of them will give you this length of this diameter, no? So having diameter dA is supremum of distance between any 2 points A, B both are in A. Having diameter less than this delta, okay, is contained in some member of script C. Okay, so what you're getting, a real number delta greater than 0 such that every subset A of X having diameter less than delta is contained in some member of script C is called a Lebesgue number. It's called a Lebesgue number for the cover script C. Okay. Now the question is, does there exist a Lebesgue number for any open cover of any metric space? And the answer is no. Okay. For example, just first consider an easy example where Lebesgue number exists. Okay, for a particular open cover. So consider R with standard metric D. It is dxy, a mod of x minus y. So we are in the R with the usual topological space. Okay, R with the usual topology. Fine. And consider the open cover. Consider the open cover script C equal to the well-known n plus 2 n in z. Okay. And you know this 0 1 2 3 minus 1 minus 2 minus this 1. If you put n equal to 0, so we are getting this. Put n equal to 1, we are getting this. Okay, so in this way this portion will be covered. Now if we put n equal to minus 1, then minus 1 to 1, so this portion overlapped. If we put n equal to minus 2, this portion is overlapped, isn't it? So in this way this portion will be also covered. So whole R will be covered by this family of open sets. So this is open cover of R. Consider open cover this of this metric space RT. Fine. Here every real number delta within 0 to less or equal to 1. Okay. 2 cannot be Lebesgue number. Why? Because if I take this set, say 1 2 3, the diameter of this is 2 or 1 to 1.5. Fine, 1.5. So diameter is no 2.5. That 1 to 2.5. That is 1.5. It is strictly less than this 2. But this set 1 to 2.5, it is not contained in some member of this, because 1 is this and 2.5 is this, isn't it? So we are considering this set, and here if we put 0, then we are getting this, and if we put 1, we are getting 1 2 3. Okay, but open. But here 1 is there, but 1 2 3, this is open, so 1 is not here, so this is not contained in this member, and no other member can contain this. So for this, though its diameter is less than 2, it is not contained in some member of this, so 2 cannot be a Lebesgue number. Okay, and we can check that if we take delta less or equal to 1, even equal to, okay, less or equal to 1, then this delta, any number within this, can serve as Lebesgue number for this open cover of this metric space. So every real number this is a Lebesgue number. Lebesgue number for this script C. Okay, for this script C. So this is an example, okay, where this open cover has a Lebesgue number of Lebesgue number. Now look at another example. So consider x equal to this set, just 1/2, 1/3, well known, 1/4, dot 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 dot. Okay, so this is a subset of R. So we can use the same tool, same metric D, to measure distance between any 2 points of this x, and we will do the same. So and the distance measuring tool, that is the metric, is this D. Okay, consider this. Okay, for all x, y in x, though it looks like this, it will give us discrete topology on x. Okay, that is, if we consider this metric, then every singleton subset of x will be open. So xd will be discrete. Okay, so interestingly, this d, this xd is discrete. I am not writing discrete metric space. It is actually discrete metric space, but it may confuse you. You are habituated to say this kind of metric space is discrete if d is defined in this way, that dxy equal to 0 if x equal to y, and dxy equal to 1 if x not equal to y, but it is not like that. Okay, so I am just writing this is discrete. That is, here every singleton subset will be open. So every subset will be open, because any subset can be written as union of singletons. Every singleton is open, so it will be union of open sets, so whole thing will be open. Fine. So here every subset is actually open. Okay. For let us consider any singleton subset of this. For okay, let us consider any singleton, any singleton subset, this 1 by k, this of x. Fine, we'll show this is open. Actually it is very easy. Actually we can look into the method topologically also, not in only metric space. So this is, say this is 1 by k, and this is 1 by k plus 1, and this is 1 by k minus 1. Obviously the distance is smaller than the distance, very easy, that if you plot this number, say 1, then half, then 1/3, then 1/4, the distance decreases, isn't it? So this, and this distance is this minus this, that is 1 by k into k plus 1. So if we take an open interval like this, 1 by k middle point, and this length, this, so this point is 1 by k minus this, we will get 1 by k plus 1. Okay, and this point is 1 by k plus this. Okay, so this is an open set in R. So this intersection, this x, will be open in x. Okay, but this intersection just contains one element. Okay, so this singleton 1 by k is open here. Okay, I am showing the fact that this singleton is open in some other way. Actually, let us consider any singleton subset. Okay, okay, then you can check this open ball BD centered at 1 by k, having radius 1 by k into k plus 1. You can check this open ball will be actually singleton 1 by k. Very easy. Okay, this being an open ball, so it's an open set. Okay, so this is open set, open in this matrix HD. So every singleton is open. Okay, I need only this fact, every singleton is open, so it is discrete. Fine. Okay, so now consider the open cover script C, collection of all singletons. Okay, n in n. Okay, this which is an open cover of this matrix space HD. These are open sets, we have proved just. Fine. And x is just 1 half, 1/3, 1/4. So if we take all, we'll get x. So they will cover x. Okay. So this is an open cover of this matrix space HD. X is within bracket 1 half, 1/3, 1/4, dot dot dot. And D is mod of x minus y. Fine. Fine. Now let delta greater than 0, any. Okay, then there exists a natural number L such that 1 by L is less than even root of delta, square root of delta. Okay, now let's consider this set A, double done set 1 by L, 1 by, taking the help of this L, 1 by L and 1 by L plus 1. Fine. And find its diameter. It has only 2 points, so their distance will be the diameter, isn't it? So d of 1 by L comma 1 by L plus 1. So mod of so 1 by L minus 1 by L plus 1, that is 1 by L into L plus 1. The 1 by L into 1 by L plus 1, both are less than root delta. So this is less than root delta into root delta, that is delta. So diameter of A is strictly less than delta. Fine, this delta. Okay, but diameter, but there is no element in this open cover that can contain this A. That is, this is a set having diameter less than delta. Okay, and which is not contained in some member of script C. Okay, so this delta cannot be a Lebesgue number for this open cover. Okay, but A is not contained in some member, not some, in any member of script C. Okay, so delta greater than 0 is not a Lebesgue number. It's not a Lebesgue number for script C. Since delta is arbitrary, so no number is a Lebesgue number, isn't it? Okay, since delta greater than 0 is arbitrary. Okay, So for QC, there is no Lebesgue number. There is no Lebesgue number. Okay, next question is, here we have seen that for in some metric space, okay, and for some open cover, Lebesgue number exists, and here we see that in this metric space, if we consider this open cover, then it has no Lebesgue number. Fine. Now the question is, okay, the question is, in what kind of, in case of what kind of metric spaces every open cover has a Lebesgue number. Okay, corresponding to every open cover there exists a Lebesgue number in what kind of metric spaces. So if we will discuss this fact in the next clip. Okay, so keep watching. Thank you.